So this video is on section 3.5 from your textbook, which in your textbook that's titled as absolute, maximum, and minimum. And in section 3.4, you guys were identifying relative maximum and minimum values, also known as relative extrema. And the word that you could have switched with relative was local extrema, right? Relative and local are interchangeable, just depending on who you're talking to or what textbook you're looking in. Now, absolute extrema also have another name, which is global extrema. So global maximums, global minimums. And you should be familiar with both of those terms. So this entire section is going to be about finding global or absolute maximum and minimum values. Okay, so just extrema, the definition of extrema, there's two different types of extrema. So there's the relative, also known as local extrema, and that refers to relative maximums and minimums. So remember, wherever the graph changes from increasing to decreasing is considered to be a local maximum value or relative maximum value. And wherever the graph changes from decreasing to increasing is referred to as a relative minimum. Now, absolute extrema refer to the absolute maximums and minimums for a function, or also known as the global extrema. So the very largest value of the function and the very smallest value of a function, right? Relative or local extrema kind of referred to the largest or the smallest value in that neighborhood of the function, right? If you could create an open interval around the point, allowing the graph to change from increasing to decreasing or decreasing to increasing. But when we're talking about absolute extrema, we're talking about the very largest value of the function and the very smallest value of the function. Okay, and here's our more formal definition for absolute extrema. Right, so if C is in the domain of F, and for all x in the domain of F, we have f of C greater than or equal to f of x, then f of C is called the absolute maximum of the function. And all that means is f of C is the largest output, right? The largest y value of the function. And that value will be the function's absolute maximum. Now, the absolute maximum can occur multiple times, right? It can occur at multiple points, but the very largest y value would be referred to as the absolute maximum value of the function. And then if f of C is less than or equal to f of x, then f of C is called the absolute minimum of the function. So again, the absolute minimum, just like absolute maximum, can occur at multiple points, but the absolute minimum value for the function will be the very smallest y value. And it has to actually be a y value, or a value, a number, right? It can't be positive or negative infinity. Those are not considered to be extrema. So differentiating between the types of minimum and maximum values. So I've kind of already addressed this, but this just kind of summarizes nicely the difference between absolute and relative extrema. So you can take a look at that. And then here's just a little picture to give you a visual of the difference between an absolute maximum and absolute minimum. Now, absolute max and min, I think, is pretty easy to identify, right? When we're talking absolute, it's just the very largest value and the very smallest value. So looking at this graph, you can see that this point right here, where x is equal to d, right? So that point, if this function where y equals to f of x, that point right there would be d comma f of d. Okay, so that point would be the point where the absolute maximum value occurs. And that's because it's the very highest point on the graph. F of d would be the maximum value. So the absolute max I'm abbreviating absolute with ABS. The absolute max would be equal to whatever f of d is. Okay, and then for absolute minimum, it's going to be the very smallest value on the graph. So down here, where it looks like x is equal to a, right? So that point would be a comma f of a. So the absolute minimum value, that would be the point that describes the location of the absolute minimum, but the actual absolute minimum value would be equal to f of a. Okay, now relative extrema, which we talked about in 3.4, relative maximums occur wherever the graph changes from increasing to decreasing. So we have a relative maximum at x equals to b, so that point would be b comma f of b, right, where f of b would be a relative maximum, but it looks like on here we have multiple relative maximum. And then the point where our absolute maximum occurred at d comma f of d, that is also a relative maximum because the graph changes from increasing to decreasing. So that point is actually the location of both a relative and an absolute maximum value. And then there's a relative minimum when x is equal to c, so that's the point c comma f of c. So the relative minimum, right, where the graph changes from decreasing to increasing would be f of c. Okay, and this graph is only defined from A to E. You can see there's no arrows indicating that the graph extends. So its domain would be from whatever A is to E. Here I can just state that on here. Maybe we'll reference this again. Okay, so the absolute minimum is at a comma f of a, absolute maximum is at d comma f of d. So we're going to figure out, looking through a few examples, how it is that we can identify absolute extrema. Right? You already know how to identify relative extrema. We want to figure out how to identify absolute extrema. So we're going to work or look at some graphs that we're already familiar with, and we're going to identify both the absolute and the relative extrema for those graphs over the given domains that we're being asked to graph for. So for this first example, we're going to examine the graph of f of x equals to x squared from -1 to 2. So that's just the parabola, y equals to x squared. I think I'll use blue actually. Okay, so from -1 to 2. So we would have an endpoint at -1, 1, 0, 0, 1, 1, and then 2, 4. Those are just some points that I can use to graph. Remember, there are still infinitely many points between -1 and 2, but those are just the points that I can use to graph. Okay, so looking at this graph, we can see, let's talk relative extrema first. So I can see that the graph goes from decreasing to increasing at 0, 0, which means that there would be a relative minimum, and I can also refer to it as local minimum. I'm going to use relative just since the actual question used that term. So there's a relative min at 0, 0. Okay. It doesn't look like there is a relative max, right? There's nowhere that the graph on that interval changes from increasing to decreasing. So there's only a relative min. So now let's talk about absolute extrema. And it looks like the absolute minimum also occurs at 0, 0. Okay. And the actual absolute minimum, which is also the relative minimum, is 0, right? It's the output, it's the y coordinate for the point. Here, I'll use a different color there. So we could say that the relative slash Also, the absolute min is 0. Okay, and then it looks like the absolute maximum, right, the largest y value, the largest output value is at 2, 4. So that would make 4 the absolute max. And it's very important that you differentiate between the location that describes where an absolute or relative extrema is on the graph of the function versus like what the actual value is. And the actual value will be the y-coordinate. Okay, so we identified the absolute and relative extrema on that interval. We're going to come back to this in a couple minutes. Okay, so next, same function, but graphed on a different interval. So graph from -2 to 2. So we'll have the point -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. Okay, let's talk relative extrema first. Again, we still have a relative min at 0, 0. And that point also, again, ends up being the absolute min. Okay, so we can say that a relative and the absolute min is 0. Now there's no relative max. There's nowhere the graph changes from increasing to decreasing on that interval again. But the absolute maximum would be these in 2 places, right? These 2 points here, these 2 highest points would be the absolute max. They both have a y-coordinate of 4, an output of 4. So at -2, 4, and 2, 4. But there's only one absolute maximum value, right? The absolute max is 4. Okay, and then same function, but no domain stated. So that means just graphed over its implicit domain of all real numbers. Okay, so I can fit 3, 9 and -3, 9 on here. But I'm going to draw arrows going to positive infinity as x approaches positive and negative infinity. Okay, still have that relative min at 0, 0, as well as the absolute min. Right? Relative min because the graph changes from decreasing to increasing. Absolute min because it's the lowest point on the graph, the smallest y value on the graph. Right? So we can say relative / absolute min is equal to 0. No relative max. Also, no absolute max, right? The graph, as x approaches negative infinity, is going to positive infinity. as x approaches positive infinity, the graph is also going to positive infinity. So the values will just keep getting larger and larger and larger. You would not say that the absolute maximum is infinity. That's not a finite number. Okay, so there is no relative or absolute max. And we already knew that a graph could not have a relative maximum, right? That just if there was nowhere that the function changes from increasing to decreasing. But our other examples have had absolute maximums. And this is our first example that does not have an absolute maximum. Okay, new function. Between -2 and 2, the graph of x cubed. So I would have -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. I had a student years ago referred to this as the chair function. That's what I see now. Kind of like we said the cube root was like a lounge chair. This is more, the x cubed is more like a chair. Okay, so relative extrema. None. There's no relative extrema. There's nowhere the graph changes from increasing to decreasing or decreasing to increasing. I'm just going to make a note of that. I do see absolute extrema though. So there is an absolute minimum at -2, -8. Also known as a global minimum. Okay, which means the absolute min is -8. So that's the actual value. And then we have an absolute max at 2, 8. And the absolute maximum is 8. Okay, so next, let's look at the graph of x cubed. No domain stated, so that means it's implicit domain of all real numbers. Same points I graphed before, but instead of having just an ending point, as x goes to -infinity, the graph goes to -infinity. As x goes to positive infinity, the graph goes to positive infinity. No relative extrema. Again. Okay, what about absolute? No absolute extrema either. So no relative or absolute extrema. Interesting. Right? There's not one largest value, not one highest or lowest point on the graph. Okay. For cosine, I think I'm actually going to skip this one. We don't need to talk about this. I don't think this is going to help us. Okay, so what do we notice about all of these functions? Okay, and I have a little fill in the blank here. So when the function is blank and defined on a blank, then the function has both blank. Okay, so let's look at the examples we've worked through. Oops, here we go. Okay, so x squared from -1 to 2. And our focus in this section is absolute extrema. So why don't we focus on absolute extrema? So x squared from -1 to 2, we had a point that represented the absolute minimum and absolute maximum. X squared from -2 to 2, we had 1 point that represented the absolute minimum, 2 points that represented the absolute maximum, but we had an absolute min and an absolute max. For x squared defined for all real numbers, we only had an absolute min, no absolute max. X cubed defined from -2 to 2, we had both absolute min and max. Then x cubed defined for all real numbers, we had no absolute extrema. So if you notice that what was sticking out, or like what was different between like the domains and the graphs and whether there were extrema, when the function is continuous, okay, all of those functions were continuous, and when they're defined, continuous and defined on a closed interval from A to B, then the function has both an absolute maximum and an absolute minimum. I'm going to use both terms here. So absolute / global, maximum, and an absolute / global minimum. Okay, this is the extreme value theorem. Okay, so the extreme value theorem says, suppose the function f of x is continuous on a closed interval from A to B. Then the function has both an absolute max and an absolute min on that closed interval. And all the examples that we just did, the absolute max or min sometimes occurred on the interval, like somewhere in between A and B, but sometimes the absolute max or min occurred at the endpoint of the interval, so at x equals to A or at x equals to B. The extreme value theorem says if you have a continuous function on a closed interval, the function is guaranteed to have both an absolute max or min, which is helpful, very helpful. Okay, so if we have a continuous function on a closed interval, we're guaranteed to have both absolute max and min. The function does not tell us where they will occur though, or if they will occur more than once, right? So at multiple points, and an extreme value theorem doesn't tell us where they happen, right? I just kind of pointed out to you about the fact that like sometimes it was in between A and B and sometimes it was at an endpoint. Okay, so let's look at this next example. Let's kind of work out how to identify, how we can figure out how to identify. Actually, no, this example is actually just going to be an example of how extreme value theorem kind of works. Okay, so identify the extrema for the function f of x equals to 1 over x squared. You can sketch that by hand, so from -1 to 1, or if you want to plot points and use some of your pre-calc knowledge. I'm also going to graph it here. Trying to make that straight. My x and my y-axis. Okay, so from -1 to 1. Now, 1 over x squared has a vertical asymptote at x equals to 0, right? It's undefined at x equals to 0. And if I'm plotting points, there's a point at negative 1, 1 and 1, 1. And then as the function approaches x equals to 0 from the left and the right, the graph is going to approach positive infinity. And you could figure that out by thinking about like creating a table of values and plugging in like 1/2, 1/4, 1/8, right? And the values will just keep getting larger and larger. Okay, so that's the graph, a sketch of the graph of 1 over x squared between negative 1 and 1. Identify extrema for the function. Okay. So no relative extrema. Nowhere the graph changes from increasing to decreasing or decreasing to increasing. Okay. There is an absolute minimum, and it occurs at 2 points. So at negative 1, 1 and 1, 1. So the absolute min is 1. Okay, the absolute minimum value is 1. No absolute maximum, though. And you're probably like, well, wait, we just looked at extreme value theorem. We have a function defined in a closed interval, but the issue is this function is not continuous on that closed interval. Therefore, extreme value theorem does not apply. And I'm going to make a note of that. So EVT, which is extreme value theorem, does not apply because f of x is not continuous from negative 1 to 1. Okay, that's really important. Extreme value theorem doesn't apply. Therefore, we were not guaranteed to have both an absolute max and an absolute min. We ended up having an absolute minimum, but we did not have an absolute maximum. Now, we still could have had an absolute maximum. It's just it wouldn't have been guaranteed by the extreme value theorem. Now, if we changed the interval from 1/2 to 1, let me see if I can just use the same graph here. What color could I use? I use the green. Okay. So let's say 1/2 to 1. So that would have been 1/2, 4 would have been the endpoint. So between 1/2 and 1, that would be the graph of 1 over x squared. Well, in that case, there is an absolute max and an absolute min, right? There would be an absolute max. I'll write it down here. So there would be an absolute max at 1/2, 4. And there would be an absolute min at 1, 1. Okay, so we have an absolute max and absolute min, and we know that having an absolute max and min was guaranteed because on the closed interval from 1/2 to 1, the function 1 over x squared is continuous. So therefore, extreme value theorem would apply for that example. So from 1/2 to 1, f of x equals to 1 over x squared, we should have known that the function would be guaranteed in absolute max and min. So EVT applies because f of x is continuous on the interval from 1/2 to 1. You should know extreme value theorem. Like, you should understand it and know what it is. If I ask you it, which I might, somewhere, you should be able to state to me, or at least summarize, what extreme value theorem is. Okay, so just a note, the theorem may or may not hold if the closed interval contains a point of discontinuity. So like 1 over x squared, from -1 to 1, there was a point of discontinuity, so the theorem did not hold. It could have, potentially, with a different function, but it is not guaranteed. If the function is both closed on a closed interval and continuous, there will be both types of absolute extrema. That's extreme value theorem, right? This is EVT. Okay. Just because a function is not continuous at a point doesn't mean it won't have both absolute extrema in the interval that contains the point of discontinuity. It's not guaranteed by extreme value theorem. So when we know, extreme value theorem just allows us to, when we know a function is continuous on an interval, on a closed interval, we know there will be both an absolute max and min. And this is going to become really key for us, important, helpful, once we start looking at application problems. So finding the absolute extrema of a continuous function on a closed interval from a to b. Here's how we're going to do that. So you'll find all critical values for the function. So we find critical values the same way that we did in section 3.4, but critical values for the function that lie on the closed interval from a to b. Okay, so take the derivative, set the derivative equal to 0, and also determine where the derivative is undefined. Then you're going to make a table of values with the endpoints of the interval and the critical values to determine the absolute extrema. Because absolute extrema will either occur at an endpoint, or if it occurs somewhere on the interval from a to b, like between a and b, but not including a and b, then the extrema will occur at critical values, right? At values that would also end up being relative extrema. The smallest value from that table will be the absolute minimum, and the largest value will be the absolute maximum. Okay, and this is what I just said. So let's do it. Okay, so find both the absolute and local extrema without graphing for this polynomial function on the interval from -3 to 3. Well, because this is a polynomial function, that tells me that the graph will be continuous from -3 to 3. That's it. We know what type of function it is. Closed interval, extreme value theorem is going to apply for this function. So we need to find f prime. Using power rule, it would be 3x squared minus 6x minus 24. We can just solve for the values that would make the derivative equal to 0. I'm going to factor a 3 out from this quadratic. And see if I can factor it. X plus 2x minus 4, I believe. Yep. So critical values, potential critical values are at x equals to negative 2 and x equals to positive 4. Positive 4 doesn't work here. Positive 4 is not a critical value because it's not on the interval from negative 3 to 3. So we throw the positive 4 out. However, negative 2 is a critical value. It lies on that interval. Okay, so now to identify the absolute extrema, and if you want to use global, you can. So the absolute extrema, we're going to make a table. Okay, x comma f of x. I'm going to put the endpoints in the interval as well as the critical values that lie on that interval, and we just have the negative 2. I always like to label what they are: endpoint, endpoint, critical value. And then we're going to see which of these values gives us the largest function value and the smallest function value. So that means we're plugging these values into f of x, into our original function. We're not trying to see the slopes of the tangent lines here. We're trying to see what the largest value is and what the smallest value is. So plugging in negative 3, we get 18. Plugging in negative 2, we get 28. And plugging in 3, we get negative 72. So the largest value for the function is 28. So that's the absolute max. And the smallest value is negative 72. That's the absolute min. And if you are being asked about their location, so those are the values. If you're being asked for just their values, those are them. If you're being asked for the points or the location of the absolute extrema, that means that the absolute max is at negative 228, and the absolute min is at 3 comma negative 72. And then we were also asked for the local extrema. So just for practice from section 3.4, I'm going to move this over a little bit, shrink it down. So we're still on this closed interval. So relative extrema. I'm still not using 4 since the function is still defined just from negative 3 to 3. As a reminder of that, I'm just going to put negative 3 and 3 as the endpoints of my analysis line. And then I'll put negative 2 on the analysis line. And then it's just plugging in test values. So I'll do negative 2.5 and 0. Those test values I am plugging into the derivative. I want to know what the slopes of the tangent lines are at those points, or the sign of the slopes of the tangent lines. So if I plug in f prime of negative 2.5 into f prime, I get, well, I know I get a positive value. Yeah, I get a positive value. Okay, and then f prime of 0, that's an easy one to see. And remember, I just need the sign, so I kind of reasoned it out plugging the negative 2.5 in. I thought about plugging into the factored version, actually. And I know that negative 2.5 plus 2, I'm still have a negative, and then negative 2.5 times, or minus 4 is a negative, and a negative times a negative is a positive. F prime of 0 would be negative 24. That's easy to see, so it goes to negative. So the graph goes from increasing to decreasing on that closed interval. Therefore, there would be a local max or relative max at -2. And if you want to plug, well, we know what the output is for -2. So at -228, comma 28. So the absolute max is also, since it's on the interval, it's also relative maximum. Okay, and we'll do one more example. Another polynomial, this time from -3 to 0. So f prime would be -2x minus 4. Set f prime equal to 0. I don't need to worry about, since it's the derivative of a polynomial is a polynomial, I don't need to worry about where the derivative is undefined. And it looks like our critical value is going to be at -2. Again. Okay, so for identifying the absolute, also known as global, they're interchangeable. I don't care which you use. Okay, we're going to make our table again. With the endpoints and the critical value. There could be multiple critical values on the interval. These last two examples have just had one. And then we're plugging, remember, we're plugging these values into the original function because we want to know what the largest y value is and what the largest, what the largest and the smallest y values are. So f of -3 is 14. F of -2 is 15. F of 0 is 11. So that means 15 is the absolute max. And 11 is the absolute min. Okay. And you could describe the points, right? Absolute max at -215, absolute min at 0.11, depending on what you're being asked for. This question just says find the absolute extrema, so I would take that as just the actual values. But again, pay attention to what the question's asking. And then for relative or local extrema, we'll do our analysis line, closed interval for the function, so I'll put those endpoints on the analysis line, and then -2 is our critical value. Using test values. And plugging the test values into the derivative. Okay, so -2 times -2.5 will be a positive value greater than 4. So then when we subtract 4, we'll still have a positive value. F prime of -1, that would be 2 minus 4, which would be -2. So we'll go to negative. So increasing to decreasing, meaning -2, again, will be a local max or relative max. So for absolute extrema, if you have extreme value theorem will apply. You have a continuous function defined on a closed interval. You are plugging critical values in the endpoints of the interval into the original function to find out what is the largest output value, what is the smallest. Relative extrema, you are still making the analysis line and plugging test values into the derivative so that you can see what the slopes of the tangent lines are